they were measuring number of errors and lower was actually better?
Then you would
this to
say, right,
Okay.
that the other one was a better way to go about it.
Okay. But like looking at it, you wouldn't necessarily just go with the highest mean. Just you
No,
have to know
you
the
need to
scale,
know
sort of.
what the desirable thing is.
Okay.
Mm-hmm. Right. It is true that there are some scores that a lower number is a better thing than a higher number. You're right, if you're looking at number of mistakes rather than number of right things.
Can you just go back a little bit and compare, just talk about correlations and maybe give an example of like when you use a correlation, when you use this?
Whenever I'm looking for the relationship between two things,
Okay.
then I'm looking for a correlation, using a correlation. But whenever I'm looking for the effect of or a difference between,
Okay.
then I'm looking, so if I'm looking for the relationships between singing voice use and music aptitude, that would be a correlation. If I'm looking for a difference between high aptitude kids and low aptitude kids on their singing voice achievement, is there a significant difference? Then I'm looking for differences, then I'm doing a t-test.
Okay.
But could you also find a correlation between students with high and low socioeconomic status and their, I mean, could you do it, just depending on what question you were asking?
Mm-hmm.
Okay.
And the last 2 pages in our packet are a bunch of samples of studies where we're going to apply across the relationships and differences. See if you can recognize these studies. Tell me what kind of analysis you'd use. So we're going to get to a synthesis activity tonight, which was you were just asking me to do. So
Great, thank you.
fear not. All right, so look at the next one, because I think one prime practicing probably isn't quite enough. So this is kind of a stinker, because if you look down, I'm sorry about the poor photocopy quality. If you look down at the bottom, you'll see that there are 5 t-values. So there were actually 5 t-tests, because there were 5 different dependent variables. So what we have here are pediatric oncology patients and healthy control patients. And so this is one of the ones where, remember where we saw group? The 2 groups are different. They're not assumed to be like. In fact, they were specifically chosen because here are healthy ones, here are pediatric cancer patients. And then what we're looking at is whether those 2 groups are different according to defensiveness, distress, depression monitoring, or blunting, whatever on earth blunting is. That one's got me. Now, you notice that there are no stars on this one when you look at the t-values, which is why I gave you another chart. Because they didn't put the stars there, you have to look over at the p columns, the probabilities. So there was, if I set my statistical significance at 0.05 and said I have to have it be 0.05 or less, you had 4 of the 5 being statistically significant. Which one was not statistically significant? Right, because that 0.793 is a whole lot bigger than 0.05. Blunting was not quite as, if it were a matter of degree, you would say blunting was less statistically significant than defensiveness, subjective distress, and depression. But it is not a matter of degree. It's a yes or no question. So the other 4 were all statistically significant. So, how about Ashley.
Okay.
Be the researcher and tell me what they found with defensiveness.
There is a statistically significant
Difference.
between pediatric oncology patients and healthy
And the control group,
And
healthy
the-
patients,
and
yeah.
healthy patients.
And what was that statistically significant difference, Ashley?
In defensiveness.
Uh-huh. And
And
who, what, so far, that doesn't tell me much. If I just know there's a difference.
okay,
I need to know who did better, or who is more defensive than the other, which is not doing better in this case.
well, the healthy patients were less defensive than the pediatric
Right.
oncology.
Yeah, and so you could do exactly what Ashley did, is do it in 2 sentences. There was a statistically significant difference between cancer patients and non-cancer patients. This group was less or was more defensive than the other group. All right, so Melissa, to do it for subjective distress.
Well, it looks like the healthy group had more subjective distress than the cancer group, assuming that the higher number.
Yeah, right,
means-
which, you're right. It's hard to imagine that that is indeed the case, that this may be an upside down scale and we don't have any idea about that, but, yep, right. So there was a statistically significant difference in subjective distress of the cancer group and the control group. The subjective distress numbers were significantly higher for the control group than they were for the cancer group.
So we're looking at the mean here?
Yep.
Question about that. Looking at those two means and their standard deviations, it doesn't always have to be opposite of each other, because both of the low mean and standard deviation is the cancer group, where it's the
Right.
higher.
And what I recommend is that you ignore the standard deviations for now and just look at the means, because that will tell you what you really need to know. All right, Jackie, do a depression one for me.
Patients who were healthy had more depression. Is that what that is?
Maybe,
I mean, well, we don't know.
Right.
I would say maybe not, but
yeah.
than those patients in the treatment group or the cancer group, not
Right.
treatment.
Yeah,
just cancer
right.
group. Okay.
Although they may be getting treatment. In fact, I
Treatment.
suspect they are, but not as a part of this study.
Yeah. Okay.
Yeah, exactly. Okay, so Holly, talk to me about monitoring.
There is no statistical difference between students who are healthy and, or not students, kids with cancer and kids who are healthy.
In their ability to monitor. All right, Peggy, whatever blunting is, go for it.
So we're saying that it's 0.05, so this is still statistically significant for,
And let's say a high number is good.
okay, so the cancer group has,
Yeah, they were better at blunting whatever that is than,
It's actually interesting. What is it?
yeah.
It's the opposite of overreaction. It's like apathy. So like
Oh,
not
gotcha, okay.
reacting
Mhm.
to a situation in a very
Interesting.
emotional way. So anyway, sorry.
Yeah.
Relenting.
Right. All right, so I think we're doing okay. We'll have more opportunities.
Oh wait, I'm sorry.
Go ahead.
So is this their way of putting a star by giving us
The
all
p-value.
of these?
Yep.
And they gave us the degree of freedom too, so we could probably just look up that stuff ourselves.
But we don't have to, because if it was, because they gave us the p-values. If they hadn't given us the p-values, we could have looked it up ourselves.
And because we're taking .05 to be statistically significant,
Right, if we'd taken .01,
But it's possible in the body of the report that they have specified a
Yeah.
different level for
Right.
themselves.
Right.
so that's why all except the monitoring are statistically significant.
right, if I'd set
On our
if
terms.
I'd set my terms at .01, then what could we have said?
Blunting isn't
Blunting-
statistically significant either.
Yeah, right, neither monitoring nor blunting were statistically significantly different between the two groups. There was no difference in blunting and monitoring between those who had cancer and those who didn't. Is a nicer way to say it.
And what does the negative value of the T value?
Does that mean anything?
No. What it means is that if we made the cancer group the A group, the B group and the other one the A group, it's just which one we arbitrarily assign to A and B.
So
can't
when
tell
you're
you.
consulting the table, you drop the negative?
Yeah, you don't look at it, right,
Does it have good tails?
yeah.
Okay.
I feel like I don't understand, like I'm picturing a t-test, and I don't feel like I understand, like, what the X and Y, like,
Okay.
what those things are. Like how,
So, I have, whoops, that's the wrong one. It may be old technology, but that doesn't mean I know how to use it. So, here's our distribution on blunting for our cancer patients. Here's our distribution, if we drew all the little dots in here, that's kind of what the distribution would look like, and they'd all fall under that lump. Here it is for the control group. There's so much overlap here that you wouldn't probably see these as being statistically different from one another, but we don't know for sure until we actually do the numbers and look at it. So there's just a lot of overlap. Now if you did another one, this is a different factor. Much less overlap here between those two groups. But we still wouldn't, just looking at this, we still wouldn't know whether these are statistically the same or different until we did the numbers and looked it up on the critical table. If we did this, there's our cancer patients, and there's our control patients, we'd be pretty sure. I wouldn't even probably do the math on that one, and I would just say, no, I'd have to still do it because I'd have to report it. But that's kind of how they look. How teased out are those two distributions? And so we'd have all the numbers for A in that one and all the numbers for B under that one. And so that's kind of the larger picture of what some of those distributions might look like.
So, I'm very image oriented too. When you said the X and Y axis thing, it kind of resonated with me. This way is like the individual people, and then this way is how they...
The number of people.
Okay, so
Yeah.
okay.
Here's their individual score and how many people got that score.
Okay.
so those are those standard deviations. And what does the T stand for?
The T is just this weird number that you
Okay.
get to look up on a table. It has no
Okay.
practical meaning to us except as it compares to the critical value.
It'd be interesting to know what the process was
Yeah, it
to
would.
come up with this.
And there are statistical proofs. You can actually prove all of these formulas. And my statistics class was much more practically oriented. It was, tell me what button to push and what numbers I need to plug in here, because I don't care about the proof. And I remember, I don't think I ever opened my statistics book once, actually, because it was all in Greek. I mean, there were sentences, there were occasional ands and things, but the rest of it was all in sigmas and weird little letters. And it wasn't helpful. So I took really good notes in class and I understood conceptually what was going on. My son, who's a math major, is horrified at me, and I don't care. I just wanted to know what to do. I'm interested in it from the practical standpoint, not from the theoretical standpoint. And some people are interested in it from the theoretical standpoint. I say go over to the math department and take statistics. Which actually, I'm not sure I do it in math. I'd actually do it in psychology because they do it from a more social science perspective, which is where I had to take 6 statistics courses in my doctoral program. I had 12 research classes in my doctoral program.
Oh my god.
Very different.
Well, that's why you can now just be like, right? Just like, I got this.
Well, I mean, I understand this stuff, but I just didn't care about the proofs, and we didn't have to know them, so that really reduced my caring. Okay, so look, can you find somewhere in your life your sheets for differences, or whether it be on your computer or...
The design for this?
Yeah, that's one. So the good news is, we know now how to do a lot of these. How about number 1? Does a t-test work for number 1? Yeah, how do you think, why? How do you know that? Because you're looking at 2 groups, right? There are 2 boxes. You're comparing 2 means. Would it be a one-tailed or 2-tailed, you think? Yeah, probably a one-tailed because it had a control group. And it would also probably be, but not for sure, be an independent sample. Because if you have a treatment and control, at least they're for sure not the same kids. They may be matched, so it may end up being dependent, but you would have had to match them according to aptitude or match them according to intelligence.
This is a tail. This is a tail. Like the full shape, or is it half of it?
These little guys.
These little, right, that's what but I just can't understand why.
How much do those 2 things overlap is the question. If they overlap a lot, the 2 tails overlap a lot. Here they're...
But I'm just thinking about a one-tailed test with a control group.
So you have this thing, the control group.
Uh-huh.
And because the experimental group won't ever be worse than the control group, you're not going to see if they're down here. You're only going to see if they're overlapping on this tail.
Okay. I think you already said that, but it was at the beginning,
Yeah.
and,
Right,
and I just
Now
didn't
it's
understand.
context.
Okay.
Yeah.
Okay.
Yeah. Right.
I didn't feel that though. I didn't feel the. I don't think I do.
So the question is the experimental group, how far out in this direction is the experimental group? It can't be in this direction because it's not going to be worse than nothing. But is it enough better than nothing? So we're only looking at it in this side.
Aren't there some instructional
Yes, there
interventions
are.
that are okay? Yes, ma'am.
Okay, so yes, number 1 would be using a t-test. How about number 2?
Sure.
Yep.
Yes.
Uh-huh.
Two-tailed.
And it would be 2-tailed and probably independent samples, but not for sure. It would depend if you matched. How about number 3?
Hold on.
Why
Well,
is
first
Not really
not?
experimental.
Right?
Why is number 1 one-tailed and number 2 two-tailed?
Because there's an experimental group, 2 experimentals versus the
Got it.
control.
Okay.
Mm-hmm. You're right, it's not experimental, but that doesn't mean we don't use a t-test on it.
Yeah.
Okay.
Is it a t-test and why?
Well, you're still looking at the differences.
Yeah, you're
Even
still
though
looking
you
at the
didn't
difference
do an
between 2
experiment,
means.
you're
Exactly.
looking at
How about number 4? Is it a t-test?
There's 3.
It is 3, so no, it's not a t-test. You can only do t-tests with 2.
P for 2.
T for 2.
Sorry.
All right, so find something else that's a t-test. Is anything else a t-test?
Yes.
And what one would that be, Stuart?
13.
Is he right?
I think so.
Why, Josh?
Because you're comparing two things.
Yeah, because you're comparing 2 means. And what kind of a t-test would it be?
Dependent.
Correlated. Well, if it's
Yeah.
because you'd have the same group of same
It's the
people.
same group of kids where you pre-test and post-test.
Now that's confusing,
Yes.
right? Because of the word correlated,
It is confusing,
and,
but
and we don't use t-tests when we're looking at correlation.
right. I
So we can
know.
call it a dependent t-test. instead.
Yeah,
I'm not calling it correlate.
Yeah.
That's fine, just so you know what it is when you see it.
Okay.
Would this be a two-tailed or a one-tailed?
It's usually a one-tailed because the post doesn't usually get worse than the pre. The post usually is better than the pre or the same as the pre.
And you're really just interested in how much.
How much.
How much growth.
Right.
Right.
Why can you only use t-tests for 2 groups?
Because it doesn't tell you. Because there are ways to do it that are better.
Because
The next ones. You'd have to pair every pair of means. And then if you had 3 groups, you'd have to look at, is there a difference between a 1 and 2? Is there a difference between 1 and 3? Is there a difference between 2 and 3? So you'd have to do 3 t-tests. And if you're only 95% sure, then you've done it 3 times and there's a bigger chance that one of those is going to be wrong. So if you had, 12 groups where you were doing pairing of every one of them, one of those groups, if you found statistical differences, is probably just probability tells you going to be wrong. Because of all of the different pairs that you've had to do. And 5 times out of 100, it's going to be wrong. So if you do it instead, rather than in 3 different analyses, you can do it in a single analysis, then you're protecting yourself from making an error. Talk to me, Jackie.
No, I'm getting it. I am.
All right, so yeah, how about number 12? No, 14, I'm sorry. No, 14. I don't know why I thought 11 was
there
13.
was
How about
cube
14?
and everything, and I was like,
Yes.
Yeah. You'd look at the gain scores between the treatment and the control group and look at the means of the gain scores and which is better. Is there a 50?
Yeah,
How
but
about
it's
that
got
one?
3 groups.
Perfect, good. Okay. Stand up, take a couple of minutes, do deep breaths, get yourself a drink, get a beer.